This video is part 2 in a series about using simple continued fractions to find solutions to Pell's equation. We'll outline the process and work some examples. Let's get started. As a quick review of the problem statement, what we want to do is find two integers, x and y, that satisfy x squared minus d times y squared equals 1. D is given. It's a positive non-square integer. This is Pell's equation. The solution process has 3 steps. They're pretty straightforward, especially the first two. The first step is to expand the square root of d into its simple continued fraction. We won't cover the process for doing this, but please see this other video if you are interested. The second step is to calculate the convergence of the simple continued fraction. We won't go over the process for that either, but please see this video for more information. Once we have the convergence, we have solutions to Pell's equation. Specific pairs of p sub k and q sub k, the numerators and denominators of the convergence, are solutions. We just have to identify which ones. That's what the third step is about. The pairs that are solutions may be found in predictable locations within the structure of the simple continued fractions for square roots. Specifically, the pairs that are solutions may be found in the positions just before the terms that equal twice a0. Recall from another video that square roots have a single non-repeating term, a0, followed by a set of repeating terms. Within the repeating terms, all but the last one form a palindrome, and the last one is twice a0. The set of convergence corresponding to this repeating term, the ones just before twice a0, may contain the solutions. If the period of the simple continued fraction is even, then each of these pairs is a solution. However, if the period is odd, then every other pair is a solution, beginning with the second one of these pairs. I realize this third step might seem confusing, but let's work some examples. It's actually pretty straightforward. Our first example is Pell's equation with d equals 3. The simple continued fraction for the square root of 3 is 1, 1, 2, with 1, 2 repeating. We can count 1, 2 terms in the repeating part, so the period is 2, which is even. Here is a table with a set of convergence. Notice the terms in the simple continued fraction are in this row. And these are the 2 times a0 terms, which we'll be using in step 3 to locate the solutions. The rows with p and q contain the convergence. Here's a table with a few more convergence. We'll put red squares around the 2 times a0 terms in both sets to get ready for step 3. Let's talk through step 3. It isn't the p and q in the same columns as 2 times a0 that may have solutions. It is the columns just before them. So does these columns. The period is even, so the pair of p and q in each of these columns is a solution. Therefore, we can see that p and q are solutions when k equals 1, 3, 5, 7, and so on indefinitely. The solutions are 2, 1, 7, 4, 26, 15, etc. We can check some of them. If x equals this p equals 2, and y equals this q equals 1, then when we substitute into Pell's equation, it is 2 squared minus 3 times 1 squared equals 1. 1 is the result we're looking for. Pell's equation is satisfied. If x equals this p equals 7, and y equals this q equals 4, then when we substitute into Pell's equation, it is 7 squared minus 3 times 4 squared equals 1 again. Pell's equation is satisfied. This will continue for as many solution pairs as you care to calculate. Let's do another example. This time, it is Pell's equation with d equals 41. The simple continued fraction for the square root of 41 is 6, 2, 2, 12, with 2, 2, 12 repeating. There are 1, 2, 3 terms in the repeating part, so the period is 3, which is odd. Here is a table with a set of convergence. There's just one 2 times a0 term so far, but here's another set of convergence. There's a couple more 2 times a0 terms. A few cells were left blank to save a little space. We won't need those convergence anyway. The solutions may be in the PQ pairs in the columns just before the 2 times a0 terms, in these columns. But this time the period is odd. Let's look at the process and recall how to handle this. Every other pair is a solution, beginning with the second pair. So we'll ignore the pair in the column just before the first a0 term, and this column is the first one with a solution. We ignore this one, and the next column that would have a solution would be in the column for k equals 11. Maybe it is easier to see the pattern with a simpler table like this. These columns have the 2 times a0 terms. These are the ones just before it, which may have the solution pairs, except we skip the first one, so this one has the first solution. After that, we use every other one. Therefore, we can see the solution pairs are in the columns for k equals 5, 11, 17, and so on, every 6th pair. The only solution pair on the screen is 2049 and 320. The next one, which would be in the column for k equals 11, is 8,396,801 and 1,311,360. Let's check that one to see if it solves Pell's equation. If we set x equal to this and y equal to this, and substitute these values into Pell's equation, here's what that looks like. It works out to equal 1, the result we expected. Pell's equation is satisfied. We've seen one example with an even period and one with an odd period. So we've covered the two cases in the process, but one more example is still illustrative. This time, d equals 5. The simple continued fraction is 2, 4, with the 4 repeating. This time the palindrome is the empty set. There's just one term in the repeating part, so the period is 1, which is odd. Here's a table with some convergence, and these are the 2 times a0 terms. All the terms after the initial one are 2 times a0 terms, because the repeating part is an infinite string of 2 times a0 terms. Here's another table. Just like before, the solutions are not in these columns, but rather they may be found in the columns just before these. So these columns may have solutions. Based on this, every column may have a solution. Following the process, though, since the period is odd, we use every other PQ pair, starting with the second one. So we skip the first one and every one after it, which leaves us with the second column and every one after that. These are the columns with solution pairs. So there are solutions when k equals 1, 3, 5, and so on. The solutions are 9, 4, 161, 72, etc. I'll leave it to you to check some of these and confirm that they satisfy Pell's equation with d equals 5. We looked at this third example because when the palindrome is the empty set, the solution pairs are in columns with 2 times a0 terms. It might seem strange because when you pick a column just before one with a 2 times a0 term, you could expect it to be the last term in the palindrome. But if there are no terms in the palindrome, you end up picking another column that also has a 2 times a0 term. And that's okay, even if it seems a little strange. And now we have seen 3 examples, one with an even period, and 2 with odd periods, one of which has a palindrome that is the empty set. In this video, we outline the process for using simple continued fractions to find solutions to Pell's equation and work some examples. That's all for now.